you here is a marvelous piece of engineering in terms of acoustics. It can detect a lot of slight change and difference that are very difficult to put in numbers and put on graph. But there is a big thing in acoustic which calls psychoacoustics. It's everything about acoustic which are related to feeling and what impression you have about the sounds you are hearing. You go to the car dealer, one of the first impression of the quality of the car will be opening the door, closing the door. Buying a Porsche, you want to have kind of a full experience, a sport experience. So the way you design things should all align with the brand image you want to give. Sound design at Audi, they're designing the e-tron noise. You see, those are engineers with lots of headsets and basically tweaking the noise parameters and to sound it aligned with the brand image. I will change the exhaust line of my Ferrari. I still keep my V12, but I make it sound like a V8 69. Wow, are you able to do that? So you see all those blocks of simulation that are getting one after the others, and then you have the vibration, and very, very often acoustics is the last one.
Jonathan Jacqmot is an expert in acoustic simulation consulting, operating under his own firm, Quiet Consult, based in Belgium. With a career spanning 2 decades at Freefield Technologies, a Hexagon company renowned for its Actran software, Jonathan has established himself as a leading figure in the field of acoustic simulation. Throughout his career, Jonathan has contributed to numerous flagship projects with OEMs spanning diverse sectors such as aerospace with Airbus and renowned automotive brands including Audi, Porsche and Ferrari. In our conversation, we delve into the various factors shaping acoustic design, the evolving landscape of automotive sound signatures, upcoming technologies, and delve into some intriguing consulting ventures Jonathan has been engaged in.
So my name is Jonathan. I'm a mechanical engineer first. I started 20 years ago, almost. I'm 40 years old. I'm Belgium and I'm working from Belgium. I've been doing most of my career acoustic simulation. I started right after the university in a company called Freefield Technologies, which is a software editor for an acoustic finite element software. It's called Actran. And I basically spent all my career in that company. This has been then bought by MSC Software. MSC Software has been bought by Hexagon, and that's how I ended up in the Hexagon world. I quit in 2023 to found my own company, a consulting company, doing acoustic consulting and acoustic simulation consulting. So I'm still in the same world of simulation, acoustic simulation for the last 20 years somehow.
Cool. Okay. So I was looking at your CV this morning, and I've seen that you've obviously worked with FFT, the Actran developer, in a number of different roles. But I saw that you had a spell with Airbus in Toulouse. I was quite interested to understand.
So I started, let's say, for the first years, Airbus was looking for acoustic consultants, and we were somehow giving more and more resource to Airbus capabilities in acoustics and using the software we were editing. And so they were looking for, let's say, knowledgeable people on site at Airbus to support them using that software that was somehow quite new for them, even though they were very at the foundation of Actran. Airbus has been a big part of that. So I went there for 1 year, spending my times at Airbus in their offices, trying to use the software for them, for their application, try to find how we can better simulate some of their problems. I've been working on the A400, and it's the military cargo from Airbus. For big question, they were, those are propelled aircraft, which is kind of challenging for acoustics. there is lots of reason you want a propelled aircraft for military transports and these kind of things. But on the acoustic point of view, it's kind of challenging, especially for the guys that are inside of the cargo bay. It's not lots of insulation, and you try to reduce the noise level, especially if there is one guy working there. So not only being transport, but working for the load, dropping the loads by parachutes and these kind of things. There is some operators there and they need very specific treatment. So we were kind of trying to improve the acoustic insulation for those guys working there for, let's say, those flights can be long, like 8-12 hours long. You don't want to be kind of in those big propeller wash and the acoustic things. So I've been working on those kind of projects, and also I've been responsible for at least a tiny portion, because my work is like 1 year, but it's on a 5 or 6 year scale. A new piece of software that needs to be validated for the noise produced at the exhaust part of an aircraft engine. Let's say, the one that you have been looking for every day. We were working on the A380 aircraft engine, because that was the moments where they were, it was 20 years ago. So we were seeing the first flights of the A380. Very, very cool things for young mechanical engineers working for aircraft. It was very nice. And so we were developing new capabilities to really model everything that is happening on the acoustic point of view at the exhaust part. With new piece of software, very, very interesting, but lots of things that are not working, things that we don't know how it works. Let's say it was a new piece of software, basically not based on finite element. It was a discontinuous Galerkin method. It's much closer to CFD compared to finite elements, and then we were really looking at how can we model that, what kind of hardware resource we need for that. There were lots of stability issues, the kind of stuff that CFD solved a long time ago, but we were very new in those acoustic propagation methods. So lots of long nights.
Can I ask Jonathan, was that work with Airbus then part of your work with Free Field Technologies then?
Yes. I was basically still employed by Free Field Technologies, but working for 1 year at Airbus for somehow, let's say, making sure the Actron piece of software was used the best possible way at Airbus by Airbus people, and also doing, let's say, work for that.
Okay. It's interesting that you mentioned 20 years ago working on 380. I was involved in 380 20 years ago myself, when we were looking at the check stress operation for first flight, and much of Airbus's operation in the UK is focused on the wing development. So we were looking at some of the leading edge and structural development for the wing, and of course when that wing is then manufactured in the UK, not too far from where I'm sitting now. Originally, you probably know this story, but the wing went by barge from
to Bordeaux,
North Wales. Round, skirted the Irish Sea, and then is it Bordeaux, and then it went by road?
It's
to Toulouse?
No. Bordeaux, then through a canal, kind of a river, but only during summertime.
Oh, really?
Yeah, because they were not. I do remember. I hope it's not a kind of a fake story, but I heard it a few times. They needed to get them transported by maybe it was the fuselage, maybe not the wings. I don't remember, but I heard multiple times that they needed this to be summertime because the river is slightly lower, so you can go through below the bridge, which was not the case in very, let's say, winter times where the water is a little bit higher. These kind of things.
I mean, those massive European projects are incredible, aren't they? In terms of the logistics that needed to be considered. So did you see? I think they called it the final assembly line for
I visited the FAL from the A380, and it's you can imagine, I don't remember what is the wingspan of an A380, but there is 3 of them in one big room. 3 A380 next to each other's.
Yeah.
Looking there, and they build a big wall between the number 3 and number 4, which is on the other side, for insurance reasons. You know, when you visit Airbus Toulouse, there is a tour, not anymore, the A380, of course, but they explain you lots of things, and for engineers, it's really kind of every piece of information is just a marvelous information, and yeah, it was very nice. And I did visit it. So, you know, there is the MSN number. So I think it's manufacturer serial numbers. And there is the MSN 001, 2, 3, 4.
Yeah.
Those four first A380 were kept as prototype by Airbus, so they can do testing with the new stuff, with the new engine and these kind of things. So we were seeing them very often taking off, landing, and these kind of things. And once we just take lunch and say, okay, let's go between the buildings, and then we ended up in front of the MSN 001, which was not painted. It was pure out of assembly line.
Yeah, the green color. Is it the green color?
Green and brown colors.
Yeah, okay.
Both of them. Yeah, you clearly see it's not white painted. The other one were white painted, but this one is very, you can really spot it when it's landing and taking off.
Yeah.
And we were discussing, and so we see people getting out of the aircraft, and we start discussing and say, you want to visit it?
Yeah.
Sure. How can we refuse that? And we go there, and because it was absolutely not, let's say, assembled, so there is nothing commercial inside, no seats, no lining, nothing like that, and just huge buckets filled of waters. But I mean, 2 cubic meters just to represent the actual weight of all the things. And then I was looking at the cable. I don't lie, it was a huge cable like that running on one side, and it was full of very tiny piece of cable. It was kind of a huge set of cable. I say each one represents one sensor somewhere on the aircraft. It was fully equipped and basically doing lots of tests, and you see the size. It's just super wide. It was a wooden deck. It really feel like somebody hammered it somewhere. It's just so that people can put station to work with getting information from different sensors and all those kind of things. Very, very nice visit there.
Yeah, no, it's incredible. I was just thinking then, so I'm a little bit older than you, so I'm 52, and when I was 18 in college studying aerospace engineering, we had somebody from Airbus come in and talk to us about the A3XX, as it was called, and that obviously became A380, and now A380 is being phased out. So that's a full product development life cycle in 34 years. Well, they've stopped developing it, haven't they? You know, but like a 30-year development cycle, which is pretty incredible, really, isn't it? And obviously, you know, the way things are now, that development cycle for most things is nowhere near that length of time, is it? You know, so that's pretty interesting to. Yeah, I never really saw the physical aspect of it. You know, we were in a design office, so we wouldn't see the final assembly and the flying structure. So that's pretty cool that you've got that. Yeah. In terms of your CV, you've had, well, effectively most of your career with Freefield Technologies.
Yeah.
So you must have worked with lots and lots of different applications, lots of different industries. You know, can you talk in general terms about some of the stuff that you started with when you came back from your spell with Airbus then? What sort of stuff were you doing? I mean, are we still talking 20 years ago
or something like 17? I spent 1 year there. So somehow 17 years old. So when I came back from Airbus, I was So I was an application engineer. For those who doesn't know what is an application engineer in a software company, it's basically someone that is responsible to interact with customer and doing all the technical things that needs to be done with the customer that is not related to development. So I was not a coder, I was not developing the software, but I was basically using it, training people on it, showing, so demo case, these kind of things, doing some validation, either really at the very basic level, like, okay, making sure that the stuff is working as intended, but then also validation on, okay, if I put a 1 Newton of force there, I should have a 1 meter displacement there, and I know it by analytical. So, okay, those kind of things are part of the application engineer's role. And there is variation here and there, but there is, in all software editors, there is a pool of application engineers. So I was doing that. And when I came back, I basically focused on acoustic radiation of anything vibrating. So it's the field of vibroacoustics. So you have an object that is vibrating. You calculate the vibration by different kind of tools. Could be like Nastron is a very good example, but any kind of things. Could be ANSYS, could be Actron, because we were also having a structural solver inside of our acoustic solver, so we can do it by ourselves. But any vibration, I was focusing on calculating the radiation, the acoustic radiation of those objects. The most common things to do is automotive powertrain. So those kind of things, you have vibration, they are very, everybody has, let's say, every OEMs, automotive OEMs have a representation, a finite element representation of their powertrain. They applied load like cylinder pressure, crankshaft movements, all those kind of things. You will have load case that you use to calculate what are the vibration of the powertrain. And I was coming on at the end of that set of calculation to compute the acoustic radiation, and then say, okay, maybe you should stiffen that part because this piece is radiating most part of the noise around those frequencies. So maybe you should stiffen or lighten it, or maybe you should put a cover with some acoustic absorbent material, or maybe you can change this, and that, and try to improve the, or very often reduce the radiated power or the sound pressure level of that object.
And this is trying to reduce the overall noise that the powertrain is developing.
95% of the time, or 99% of the time, is to meet regulation or comfort. So there is, let's say, regulation is making a big part of any engineer work. But for acoustics, there is lots of, let's say, regulation work. So you need to be below a certain level. If you are not below that level, you cannot sell your products. Same for aircraft. If you want to land your aircraft at Heathrow in London, you need to be below a certain level. If your plane is not below that level, you cannot land there. It's as simple as that.
Yeah, okay. And do those requirements then, if we take a car as an example, are they governing the experience that the driver gets, or are they governing the external, the road noise for the houses that the car's driving past, that kind of thing?
The first one is regulation. The second big one is comfort, really end user comforts. And there, things are much more, let's say, not only, obviously you want to try to reduce as much as possible. Okay, try to have the quieter possible experience for the driver. But there is a big thing in acoustic which goes psychoacoustics. It's everything about acoustic which are related to feeling the sound, feeling and what impression you have about the sounds you are hearing. And it's a huge field of, let's say, not really engineering stuff, but psychological stuff. But it's super important.
So this is called psychoacoustics?
Psychoacoustics,
Wow, okay,
And I will give you just a very simple example about how important it is, okay? You go to the car dealer and you want to buy the car. One of the first impression of the quality of the car will be opening the door, closing the door. if you, and there is lots of people that are studying these kind of things and doing jury testing, typically. Okay, you open a car, you close the door, and this one. Okay, does it feel sturdy? Does it feel heavy? Does it feel comfortable, and so on? I got a discussion with a project in Porsche in Germany.
Yeah.
About the wheel button, steering wheel button.
Yeah.
And they were doing jury testing because the left one was feeling and sounding different than the right one.
Wow.
And this was kind of a quality issue because, okay, those are looking very similar. Why is this one is, you can press it a bit further, it sounds like a click, and the other one is more sounding like a cluck. And why is it different? Those kind of things.
Yeah.
For an engineering perspective, you see two curves on a line, and that's not about really engineering. It's about feeling, and of course, if you are buying a Porsche, you want to have kind of a full experience, a sport experience. So the way you design things should all align with the brand image you want to give. I provide a sports car, or I provide a luxurious cars, whatever you want. But there is an acoustic component to the brand image or the product image you want to put.
Wow. Okay. So again, excuse my ignorance here, but in acoustic terms, could you look at the noise emitted or what have you from a Porsche and see it be different to a Volkswagen or I'm thinking of two ends of the market, a Ferrari versus a Mini or something. Is it possible to quantify those almost those psychoacoustic behaviors so you can see them on a graph? Is that possible?
Very difficult. On a graph, it's super difficult. But you here is a marvelous piece of engineering in terms of acoustics. It can detect a lot of slight change and difference that are very difficult to put in numbers and put on graph. It's possible. It's not. It's definitely possible. But there is a lot of people, and that's the reason why we still have in lots of acoustic departments. You can look at, let's say, sound design at Audi. They published a lot of video on YouTube about designing the e-tron noise.
The
electric cars, and you see those are engineers with lots of headsets and basically tweaking the noise parameters and a few things to sound it aligned with the brand image. So you can, there is tools to kind of distinguish, but they are not really interested in that. An OEM will be interested, okay, what do I want my car to sound like? And I will not work versus the others, but I will work with the image I want to give or the sound I want to give to my customers. We got a super interesting talk by Federico or Fernando. It's a Ferrari engineer that went to one of our user meetings. He was doing a very nice all-hands presentation there. He was responsible for the exhaust lines and how let's say, the engine of Ferrari is sounding, basically, kind of a big job. And he was explaining the way, of course, there is the architecture of the engine, like if it's a V6, V8, V10, V12, the way you organize how the piston are fired. So it's 1, 3, 5, 7, or is it 1 and 2, and then the way you organize the combustion, and then how you organize the exhaust line, because the exhaust is a kind of a big flute or a big saxophone, whatever, let's say,
saxophone,
music instrument you want, but that's basically how it's working. And he was showing with all the, let's say, tools he has. He was, okay, this is a Mustang 69 organized as a V8 with this kind of parallel, and the way you organize the piping, you have this kind of sounds, okay? It is a Ferrari V12 atmospheric, and with that kind of firing and this kind of piping and how they are connected back with the distance, let's say playing a role about the frequencies, and you have a totally different sounds. I say, okay, now listen, I will change the exhaust line of my Ferrari. I still keep my V12, but I make it sound like a V869.
Yeah,
Said,
yeah.
wow, are you able to do that?
Yeah.
And then he said, no, we are starting to have our first V8 turbocharged engine for Ferrari, which was kind of something super new when he was doing the talk.
Yeah.
And I had to, he told us, okay, he was having the mission so that the turbocharge, so really kind of a big things working between the inlets and the exhaust of a V8 turbocharge should be changed or should sound like the original V12 or V10 atmospheric. And you need to scratch your head and try to find ways so that the noise is correctly getting out of the cars with the nice kind of harmonics and the difference between the harmonics and the way they are getting out, the level and so on are still sounding, the most important thing, sounding like a Ferrari.
Yeah. Okay. So two things I wanted to ask on that really that sprang to mind. Just going back to the vibroacoustics then. So thinking of an analogy like a wine, a vineyard that's manufacturing wine, they have the wine experts who can quantify the flavor or say this is a good year, this is a bad year, blah blah blah. Do the automotive companies have people with expert ears? Does that make sense?
Yeah, totally. Yes. Depending on the size of the company and how important it is.
Yeah.
I will say something like, if you are selling a Renault Twingo or an entry-level car, a small car, the important is that it's quiet, it feels sturdy, quality, and these kind of things.
Yeah.
So you are not really trying to, there is people that are focusing on that, but not really kind of super here, okay, like in vacuum or something like that. If you go on the other, let's say, side of more luxury cars or sporty cars, there is a team of 2, 3, 4 people dedicated to really hearing things.
Wow.
And it goes for the interior, it goes for the engine. Now with electric engine, it's a little bit different, but there are also people working, and you are, let's say, for those who are interested in sounds, it's more like a special effects sound design, like in cinema or movies, that are really working on those things. And Audi has published a few videos on YouTube, very, very interesting.
Yeah.
And then there is also sometimes teams for loudspeaker in the car. If you have buying a very expensive cars and that the loudspeaker option is maybe 10K, then you want to make sure that the audio quality, the hi-fi for the music is kind of top notch. So there is people that are really going the cars, listening the cars. There is specific tools in the industry dedicated for that, and you can tune the amplifiers, the position of the loudspeakers, the size, the times. Even in common cars, there is like between 6 and 12 loudspeaker in the car. It's a basic one. I mean, if you go to the higher ends, you can have 20, 25, 30 loudspeakers, specific loudspeaker for the audio.
Yeah. No, that's interesting. And the other thing, I imagine this is probably the case, that using simulation and or experimentation, a car can be tuned, like you said, to give a specific noise signature, sound signature, or what have you, based on the market, what people want to see, how it makes them feel when they're in that vehicle.
Yeah. But still, it represents a small portion. This represents 5 to maybe 10 maximum % of the use case. 90% is, okay, let's make sure the car is making at least the same noise than the previous generation and ideally a bit lower. That's representing 90% of the case.
There
is sometimes some troubleshooting It happens a few times. I've two experience in mind, German automakers saying, okay, the test pilot said he's hearing with the first prototype or the second prototype something from the rear right, and he's listening to a noise at specific speed or specific on specific road. And so, okay, what is happening there? And so they are basically putting some microphone and say, okay, we see a peak that should be hit. Okay, now we try to understand what is happening. And then you go back to the simulation model, you try to say, okay, what is happening? And I think in that case, it was kind of the fuel tank that has modified the brackets for the suspension, making a different propagation path for vibration, which makes more noise, and say, okay, we need to rethink the brackets and change it.
Yeah. Gotcha. No, that's fascinating. I mean, it's a you're still heavily involved in simulation and predict, mathematical prediction, what have you, but it's a universe away from the type of simulation that I'm involved with. It's very, very different.
And still, it's super related, because let's say that's very often how I presented how acoustic software is coming in the development line, and especially in the virtual design development lines. Often, if you are thinking back to the powertrain, very often you have some chemical simulation to make sure you have the right ratio of fuel, air, and these kind of things. And then you have a multi-body simulation with the crankshaft, the piston, and these kind of things. You want to maybe CFD simulation as well. So you see all those blocks of simulation that are getting one after the others. And of course, you have then durability for it's a Nastran simulation of the powertrain to see that nothing is breaking. And then you have the vibration. And very, very often, acoustics is the last one. It's the very last piece of software you put. And very often, you need, as an input, the output of the previous brick. And typically, the Nastran vibration or dynamic simulation. For vibroacoustic simulation, that's very, very often the case, even though there is a few other things. For aeroacoustic simulation, it's exactly the same things. The only difference is that you have a CFD solvers, which is the last brick of the design or simulation lines, and you put acoustics right after. It's very unusual that there is another piece of software after it. There is one case for acoustic fatigue where you put a fatigue solver or fatigue post-processing tools after it. But very often acoustics is the last brick, but it's really based on other piece of software. And that's the reason why I know very well Nastran, for example, or CFD solvers, because very well, I'm not an expert on Nastran, but I'm used to read Nastran model, checking output of Nastran model, just to make sure that to garbage in, garbage out. You need to make sure that the input of your model is good before running it and making sure the tools are somehow okay.
That was so one of the other guests that we've spoken to recently was talking about that sort of building block approach where a piece of work is almost thrown over the wall to the next department, but the importance of making sure that there is at least some level of understanding on the other side to say, okay, this data that we're getting is appropriate and is correct, and there's no inherent errors or biases that are going to influence what we're doing. That's a big thing. Yeah, cool. Okay, Jonathan. So that was I suppose a very, very big introduction and background to your own experience and the some of the ways that acoustic simulation is used in a number of different companies. I mean, a list of questions here. One of the questions that I like to ask people to sort of try and dig in to what it's really like at the at the coalface, as we say, the people actually doing the work. What are some of the best things that you've seen done with simulation, and then equally, what are the worst things or the areas where there's the most likelihood for error, or where people are just using simulation almost blind and getting, you mentioned garbage in, garbage out. Are there any areas where you see those kinds of things? So yeah, again, big question. one end, what's the best usage and what's the worst usage that you've seen in your experience?
Best usage. So it's very dependent on what let's say. My job was, I'm not part of the industry doing cars or aircraft or these kind of things. So
yeah,
I'm really on the software editor company, and that might somehow play a role. There is a few
okay.
cool,
Yeah.
But I think there is good things also to because I've been able to touch a lot of different topics. One of the things that I've really appreciated is a project that some of my team performed at Ferrari. I think it has been published. It was a method so that we can filter and tune which kind of noise was getting inside of the car. It was a feedback from the test pilots there. They were, let's say, the way we have been able to damp the noise and making sure that the noise is not coming too much inside of the cars was very good. So the levels were much lower, but we have lowered a portion of the noise that was kind of super appealing, the kind of sporty things, the kind that is raging and pushing and really feeling the sensation, the emotion of a Ferrari. And we say, okay, we need to develop. So we basically damn the noise very well, maybe too well. And we need to bring back a portion of the noise, but the portion of the noise that is getting all those emotions.
Yeah.
And the team has been developed a kind of a filter or silencers that you can tune to make sure only a portion of the frequencies were able to go in and the other were not able to go out. It's kind of a passband filters, but actually done. And it was maybe 10 years ago, and it was the beginning of those 3D printers and these kind of things.
Yeah.
And in 1 week, I remember that was kind of the mind-blowing things. It's like, okay, they've been able to understand the problem, design the filters, optimize it just for the frequencies they wanted to. So changing the shape and automatically doing all those kind of things. Then 3D printing the piece, putting it in the car. Of course, you can do that in small manufacturers like Ferrari. Then ask the test drive, the test pilots to, okay, let's go to Maranello, make 3 rounds there, come back and tell us what you feel. And doing that 2 or 3 times, 3D printing a new piece of filtering device, I will call it, and then changing and the test pilot, okay, that's much better. Or no, I was too low on the low frequency bands and too high on those one, and trying to tweak the things. And these kind of things, when you see, very often I was kind of far away from the final products because I'm on, let's say, I'm behind a desk with computers and having, let's say, being able to see, because I've not been working directly myself on the project, but seeing all the interaction and see how things were going and the test pilots and all those kind of things. That's super cool. That's the kind of things you really like.
Yeah. I mean, that's something that I, the projects that I really enjoy is getting that feedback loop when the simulation is directly influencing the physical behavior. And doing it quickly. I mean, going back to the Airbus, stuff that we're talking about. You could spend months and months and months and not see anything come of it. Whereas, so to summarize what you just said, then, so you would have maybe the vibroacoustic performance of the interior of the vehicle, and then you would 3D print pieces of optimized structure to give you the noise signature that can then be physically tested, and then the loop comes back from the driver with the ear or the microphone or what have you. Okay. That's a pretty clever and also satisfying loop.
And the turnaround of 1 week, because very often I've been working on, let's say, on designing the carpets or the headliners inside of cars. They don't make 5 or 10 prototype of those. Okay, we will do one. You have to decide, and we hope it will be the best. And so you design something, and then you have basically a design that you want to produce. Then it's go to purchasing department that they will try to find suppliers. The suppliers say, okay, we can do something that is somehow related to what you designed. And then they provide you one sample, but it's not exactly the final products, and it's tested on the car, which is not the car you designed for, but another one, because they don't have a prototype of the car. And you see, and this is happening on 6 months. When I've done the design of the parts, 1 month after, I'm on another project and doing something else. So I have no idea of will it be good, how this is because I'm part of this, let's say, a software company doing consulting at that times. But I guess the people that were really in those departments have feedback, and then, but this was not part of what I've experienced in my group.
Yeah, understood. Yeah, okay. Now that's a really good example, and I can visualize that straight away, you know, in terms of what's going on there. Okay, what about, difficult, but you know, areas where people are using acoustic simulation maybe in a not particularly optimal manner, or areas that are prone to mistake, or you know, what sort of stuff do you see, or if anything, along those lines?
Oh, there is maybe 2 things that I've been seeing. First is an inadequate usage of the software capabilities. Basically, they have something to do. They do it one way, but in this, let's say, in action software, that's the one I know, it's more like a toolbox, and sometimes there is multiple ways of doing the same things. You can use different approach, different solution sequence, different solvers, different boundary condition to achieve the same rules. And once I went to a customer in the US doing something kind of high precision, so you need a kind of a big accuracy. So they were using like, okay, you will be 20 element per bending wavelengths, or this kind, because there is really wanting to go in the details. So there is basically producing huge model, problematic. And then they were using kind of the wrong solvers for that specific application. So it was running, but like in 1 week instead of 1 hour. And then I visited them.
And specifically from an FEA standpoint, it's to do with how much theory or how much understanding people need to have to use the simulation tools that we have available to us. You know, do people need to be experts in everything that they do, or can they be multi-skilled, that kind of thing? You know, for me, I think personally, to be a good practical simulation engineer, or to use simulation in the design development process, you need to know the fundamentals, but you don't need to know the minute detail of every single thing. As long as you can use, you know, check your assumptions, check that what you're putting in is giving you good quality out. You know, I mean, it sounds to me that the workflow you just described with your US customer or what have you, perhaps didn't have that level of understanding. So how much do people need to know about the theoretical background to be able to use the tools productively?
For me, on an ideal case, you should have a good understanding of the mathematics behind the software you are using. Like you are doing dynamic simulation in a finite element framework, you need to know FEA, you need to know structure dynamics on the theoretical point, at least a portion of it. How big to be discussed, but at least you need to know what is a natural boundary condition, what is an essential boundary condition. You know, those kind of things that create huge problems in the way you do your models. Okay, you need to know a portion of it. Clearly, you need. And then something that is sometimes not really addressed is the philosophy of the tools you are using, the way it has been designed and made from the background. Meaning, there is example in Astron or in Actron. In Actron, you have components, you have domains, you have material. Those are the essential building blocks of creating a model. And all the software, the pre-processing, the post-processing, the solvers, they are all based on those big concepts, whatever they are, those concepts. And you need to understand really clearly why those concepts are different from each other's and how they complement. Are they orthonormal? Are they complementary? Are they subsets? These concepts is only part of this one. If you really need to know, because this will give you a much wider understanding of what you are doing in your software. Okay. In for example, in NAS, when you have A set, S set, all those kind of things, and those concepts are sometimes very interesting to know, to better understand what you are actually doing. What this boundary condition is doing is basically removing that degrees of freedom or these kind of things. Right hand side, left hand side, those are concepts that you need to, it's very interesting to know. That being said, I spent a lot of times in my previous, let's say at Hexagon, at Freefield Technologies, trying to make sure that any beginners will be able to use the software. So I'm telling you that you should have that, but I spend a big part of my times trying to improve the ease of use, let's say reduce the cost of access to doing acoustic simulation. You want that, and typically this is the case for acoustics, but I guess it's the same for many others. I will have lots of companies just cannot buy or hire an acoustic numerical specialist. So you need to convert the dynamic guy to acoustic, or you need to convert the CFD guy to acoustics. And so we were trying a lot of times to focus on trying to make things easy for them. So they don't need to spend 1 week of training or 2 months of training or 2 years of training to understand everything. So on one side, you need to know things. And on the other side, all the software editors will try the maximum to ease you to get there. So you see, it's kind of a little bit.
It's a balance, isn't it? It's a balance. Yeah. You know, you've got the, you know, ease of use and, you know, contemporary user environment and what have you to slicken up the workflow. But ultimately, you know, if you've got a black box and you don't really know what's going in and what's coming out and be able to verify that that's working, it is difficult, isn't it? You know, yeah, fundamental building blocks are still massively important, aren't they? You know,
we used at, let's say, when we were having these discussions, typically we have those discussions with either the interface manager, the guy that is basically trying to create a good interface, but also the product managers in software editors. That's typically discussion you have. And we were always asking ourselves, okay, what is the value for the users, the customers, the users, to know that? Isn't there a way that we could do that for him? You know, meshing criterion. If you know the frequency, most likely you should be able to deduce what should be the meshing criterion. So is there any very important things that you need to understand? Of course, the user should know that you need a certain number of elements per wavelength, and the wavelengths will depend on the frequency and the speed of sounds for acoustics and these kind of things. So there is fundamental that you should be aware. But then in the user interface, if you ask it to mesh a cube of air, you know the maximum frequency because you already introduced it somewhere. Should we ask the users to put the element size he wants, or should we simply assume it? And that's the kind of question that you need to answer on not on a daily basis, but almost when you are developing those kind of solvers.
I mean, with all of these things, it almost makes it does make the verification at the end, or you know, during the process, it makes the verification of what you're doing so important, doesn't it? You know, that's key, isn't it?
Yeah.
You know, well, a couple of things I'd like to talk about, you know, before we finish is, where do you think? I mean, I wouldn't say it's a cliche or, you know, a keyword or what have you, but where is, you know, data science and AI and machine learning presumably helping with acoustic simulation, and what kinds of things are being done to help out, for stuff that's current and also in the future?
So I've been involved in several projects in AI. I think we can somehow, let's say, that's how I structured things in the company before. There is somehow three things we can do. First is to ease or to improve the usage of the software. We did one project, so that's basically we were monitoring all the calculation that has been done for the last 5 years in the company. And we're looking at what are the information about the model, what are the information about the hardware, and basically trying to create a small tools that you create your model, and at the same time you will have what will be the calculation times that is predicted if you put this, and or what kind of machine you would need that amount of RAM. And so this is basically really data mining and these kind of things to try to ease the usage, or maybe automatically set a boundary condition, or maybe those kind of things that are embedded that users doesn't care. But that's basically improving everything. Could be for meshing, could be for whatever. That's a big class. Lots of things are done every day on those kind of things, and in all the softwares I'm aware. For the engineer, there is a second big class of things is basically doing reduced order model. Basically, you need to do powertrain, you do 100 of them. And so that's you try to extract information from those 100, and then maybe if you want to do the next one, it will go, let's say, AI, machine learning algorithm will be able to predict much faster than if you have to do. That is a fancy, I'm a little bit exaggerating there, but a fancy, let's say, linear, let's say, deduction tool. Okay, you have those kind of case, and then you try to deduce what will be the result for another case. It's working marvelously well. It goes super fast. There is one big thing about those kind of analysis, very nice for optimization, by the way, of course, is that oppositely to other big data or machine learning algorithms, if you go to Amazon and all the data Amazon has, the data is free. It's based on the purchase that everybody is doing. So the data is free for Amazon. You just work to dig information from those free data. Okay? In simulation, data is expensive. To be able to create a kind of a reduced order model of your powertrain, you need to run 100 of them. And so that you need to run 100 so that the next one is very cheap. So you need to find a case. And you see how different is the approach in simulation, machine learning or data scientists and this compared to other kind of companies. And so we need some specificities to go there, but it's working very well. I've done work of optimization there, very top-notch, really kind of real-time solution and these kind of things. So very, very, very nice things. But for me, it's working well, but it's kind of a fancy reduced order model building. Working well, but nothing more than that. I think that there is a third way of doing or using AI, because it's doing AI, it's using AI. And it's basically based on the talk that the CEO NVIDIA provided very recently. He said, thanks to ChatGPT and all those kind of things, there is lots of people that are now able to do programming without having a proper programming masters or coding, learning or training. We have been able to give access to these kind of technologies to a much wider, and that's something I experienced because I have a side project where I need to code in C, and my C learnings is back at the university. You go to ChatGPT, I need a function that is able to do that in the data, is writing it, you testing, is verifying. I think that one day, maybe, hopefully, we will be able to ask a kind of ChatGPT like to say, okay, I need to calculate the the failure of a bridge. What is the maximum weight I can put on that bridge? And it will tell you, okay, that's very interesting. Here is the different methods you can use, analytical solution, FEA solution. And then it will drive you, say, okay, I like the idea of doing FE. Okay, what do I need? Okay, you need the geometry, then you need to mesh it, then you need those kind of material properties, and here is the things. And, you know, kind of something that will be able to guide you. And you can see that on the very wide things, so you don't know, but even in your own software, okay, Actron can do transmission loss, powertrain radiation, can do aeroacoustic simulation. You could maybe ask your software, okay, I need to address that specific topic. Here is the information I have. What do I need more? And you know, something that is guiding you and give access. You remember, and then engineers will be back and say, okay, that's a black box. I'm listening to a machine that is as smart as it's still a machine. And so it's very going back to your first question, say, okay, how much theory should I know about? But still, I think it would give concept and access to the
to summarize or to just overview what you've just said then. So the second approach that you mentioned, which is sort of where we are now in terms of using many simulation runs to develop a reduced order model understanding that can then be used in a near real-time manner for digital twin, for asset management, all that kind of stuff. So you're saying that the data point creation where we stand today, even though we've got these very clever tools that will work with that data, the generation of the data is still very expensive because there are many FEA models that have gone into generating that data. Okay, the next step, the third step as you described it, is whereby the AI or the machine learning aspect of it is there to help with that original data point generation, if you like. So you're using it in a manner, and you know, you can use the term black box, but you could also use the term tool, couldn't you? You know,
sure.
Nastran
toolbox
in some ways is a black box, but it's also a tool, isn't it? You know, so it's almost like you're using the AI to, I mean, Nastran is today's language, or Actron is today's language. 50 years time, 100 years time, it'll be a different language, won't it? You know, but using those machine learning algorithms to effectively populate that simulation data point set in a manner that we can't even comprehend at the moment, to then feed into the next level of learning, if you like.
Also there is a big part of guiding someone that is inexperienced in the simulation, or like a dynamic structural engineer that is starting need to do acoustics and that need to be guided, and you need to get a first foot in the place and then supporting you going further and further in your exploration of acoustic simulation.
I mean, I'm just thinking back to where FEA or Nastran has come from. You know, if you're meshing a curve, you know, a fillet, a piece of fillet geometry, 50 years ago, somebody would have had to work out the physical coordinates of those points to get that curve. You know, we don't even think about that now, but that's, you know, so we black box that geometry aspect, and we take it as, you know, we can see the curve, so it must be right. We don't even question that, do we? You know, it's the other stuff that we sort of question at the moment from a verification perspective. So what you're saying is that the AI tools will just grow out that support or that understanding in a way that we don't need to think about them at that level either, you know.
That's somehow what I hope for. I don't know if it will be possible. I don't know if it's, I know people are working on that. Will they be successful? I don't know. I really know that we are able, the second part, the second pillars, I know this is ongoing. We already done successfully and so on. The next one, I don't know. I would be glad to see it. And to be honest, when we see how things are ramping up in AI, it might be next year or in 2 years. But
Yeah,
sometimes you don't know yet the limitation of the AI capabilities, and maybe it at one moment in time is okay, this will never be achievable with AI, and for good reason, and that you will learn those good reasons later on, and we don't know. But I hope that we will go to up to that kind of point afterwards.
Yeah. One thing that perhaps I'd like to finish on, in terms of the conversation that we're having here, I've seen again from your CV that you've written a number of research papers. So you're looking into applications of technology, new technology developments, how these things are affecting the companies and the clients that you work with. I mean, have you got any particularly interesting projects on the go at the moment, or stuff that you're looking at in the pipeline? Obviously, we need to respect customer confidentiality, so obviously we can't talk too much detail, but what sort of stuff are you working on?
There is a few projects that I've been doing that have been very interesting. A big one that is interesting. I remember because it's the first time I've been able to look at my model from Google Maps. So I was doing a project in Germany for people that were building facility to test aircraft engine. So you build the aircraft engine, then you put it inside of a building, and you throttle up, throttle down, and you try to test it. And of course, after a big repair, you also need to test it back. And it's a big building, like 100-meter long, with those huge air intake and obviously a huge exhaust line.
Yeah.
But you can see the building on Google Maps.
Wow.
We were doing a project because we were trying with a recent new engine that they were testing.
Yeah.
The research department that was in the building in front of that building, in the testing buildings, when they were putting full throttle, the guys were not able to work anymore because of the noise.
Oh, wow.
And so we came up and said, okay, here is the problems, here is the big buildings. We put a big engine, we put at maximum power, maximum throttles there. And of course it makes noise, makes sense. And we need to make sure that the noise is getting lower to a certain level, because the engineering team in the other building on the other side is not able to work. And so we have to work on Sundays and Saturdays, and the cost is getting bigger. And so, and we were defining kind of a set of French fries of foam. And obviously you have kind of problem, because you don't want to disturb the flow too much, because the flow should arrive naturally to the air intake of the engine, of the aircraft engine. On the exhaust side, it's super hot, so you cannot put acoustic treatment that are melting, and all of this is very low frequency. And in acoustic, low frequency is kind of a nightmare to treat, because low frequency means a long wavelength and a few meters. And so if you want to damp those low frequency, large wavelengths efficiently, you need also to put in front of those wavelengths similar size of acoustic treatment. So if you have at 34 hertz, you have a 10-meter wavelength. So you need to put at least 5 meters of foam. And so you need a lot of room, and you go in those kind of things. But I really like to start the presentation of the projects by Google Maps, and you're zooming. Okay, here is what we are going to work on.
That's incredible. I've never ever thought about describing something. Can you see this project from Google Maps? That's pretty cool. That's pretty cool.
It was a very nice one, and a nice project again. I've been able, the opportunity and the chance to do it on site and seeing the infrastructures and walking the buildings there. So very, very interesting.
So you've essentially been filling the volume with material, moving material in the volume to change the vibroacoustic or the acoustic frequencies that are coming out of the building.
Exactly.
Yeah.
And trying also to, of course, you have an inlet and an exhaust line. It's okay. What if I'm changing the shape, if I'm trying to orient the noise in one direction versus the other one?
Yeah.
And of course, before asking a construction team to spend 2 weeks and shutting down the facility and building walls and then saying, oh, by the way, it's not changing anything because the frequency that are involved doesn't care about the shape at the end.
Yeah.
And you can do that in your simulation tools in 1 hour or 2 hours.
Yeah.
Then you see really the usage of
Wow.
simulation in those cases. And in fact, it was the case. You can change whatever the shape of the inlets. The low frequency doesn't care about the shape. And so you need to work on absorption material.
Are you? Yeah, okay. Well, I think you mentioned there absorption. Are you interested in the actual structural behavior of the frame of the building as well, or is that not really?
No, it was kind of rigid. It was kind of a concrete, and so for acoustics, we were not taking care of that. We checked, but if you have 20, 30 centimeters of concrete, it's not that part because you have an opening of 4 meters by 4 meters that is open air. Noise will go through that and not through the 30 centimeters of concrete.
Yeah. No, that's amazing. The structure on Google Maps versus the Ferrari 3D printed loop.
Oh yeah.
You know, two extremes, but massively important for both, for the product development, both conditions, isn't it? You know, cool. Okay. Anything else, just briefly, that you want to talk about?
I could spend a whole weekend discussing with you, a whole night discussing with you all the kind of stuff. Yeah, that's a lot of projects. But those, I'd say, that's a representation of some of the things we have been able to do, and that I really enjoy doing for the last 20 years, and most probably for the next 20 years as well.
Yeah, no, that's amazing. I mean, one thing I'd like to ask you, and you know, I'm in consultancy myself, obviously in a slightly different field. Do you tend to have longer term client projects, you know, number of months that follow on from one another, or do you have things overlapping and have to manage that stuff as you go along?
I'm working much more on the overlapping size, like doing one project and then another one. What is happening is sometimes on let's say development cycle, they will need multiple iteration of simulation step. So you do a first design and working, of course, a few iteration days, and then then there is a testing campaign for like 1, 2, 3 months, and then you come back to the topic and work. Or especially in consumer electronics, you do the first one. It's produced like a cell phone because there is also loudspeaker, microphone, and it's kind of a very important part of a phone. Smartphone, not the only one, but you do the 2018 version, and then the year after say, okay, we changed the battery or we changed the microphone stuff. This is affecting the way we put the ear ducts, and so you work on the second version or the 2019 version and 2020, 2021, and you basically iterate. However, let's say, especially in my previous job, I was much more interested in selling the software because we were a software editor. So the final goal somehow was to sell the software so that the engineers are doing the projects by themselves with the software. Now I'm much more on the consulting side, where I try to focus on customers that will come back to me and request me to do the new version. It's a slightly different point of view. But still, it's on the same sort of discussion.
Understood. I mean, I'm involved in consulting and selling software and development of online training as well. So I have lots of different hats that I can wear, you know, depending on who I'm.
What I have always realized is that whatever hats, whatever business model, whatever, happy customers will be the best things you can do. So even if it's somehow killing a little bit your business because you train them, you show them how to do that by themselves, they will be happy. Of course, they will do maybe things by themselves, and you are basically reducing the work that you will have with them. But in the end, they will ask you something different, something that you know that they don't know, and then you will do something else. So whatever hat you have, is the final satisfaction of the customers is the end goal.
Good stuff, Jonathan. Thank you. Well, like I say, we've covered a lot of stuff there. I've learned a lot. You know, I mean, I did wonder whether to ask you about the noise that my Audi door, you know, was going to make when it shut. But you've talked about that, and you talked about some other fantastic stuff as well. So, thank you, Jonathan. That's been great.
It's been a pleasure for me as well.